Today I'm going to be talking about the cut dimension of a graph, and this is joint work with Tongyoung Lee, Miklos Senta, and Xingyu Zhang. So all the graphs in this talk are going to be undirected and weighted, and we represent a graph by a pair, v comma w. So v is just the set of vertices, w is a map from all the two-element subsets of v to the non-negative real numbers. And we say that the edges of G are those pairs of V that are mapped to a positive number under W. Okay, so those are graphs. We're going to be talking about cuts in graphs. So a cut in a graph is defined by a subset of V that's not the empty set and not the whole universe. And that set defines a cut in the following way. So the cut defined by that set is just a set of edges with exactly one endpoint in that set. And we'll denote this set of edges as delta S. Okay, so a cut is a set of edges, the set of edges with exactly one endpoint in the set S, and we call S the shore of the cut. The weight of a cut is just the sum of the weights of all the edges in the cut. Okay, so here we have a little example. So this is a graph that I'm going to be using as a running example throughout the talk. So the black edges here just have weight 1, the red edges have weight 2. So if we take the set 3, 4, this defines a cut, and the edges in that cut are going to be edge 1, 3, edge 3, 5, edge 2, 4, and edge 4, 5. Okay, so those are all the edges with exactly one endpoint in the set 3, 4. And the weight of that cut is going to be 4, because there's 4 edges leaving the set, they all have weight 1. Okay, and you can see from this picture that if I were to remove those edges in the cut, that would actually disconnect the graph. Okay, so here's just one more example, another example that would be important for us, where shore just has a single element. Okay, so we call such a cut a star cut. So in this case, the edges leaving the cut the edges in the cut are going to be 2, 4, 2, 5, and 1, 2. And this cut also has weight 4 because it has the red edge has weight 2, and then 2 edges of weight 1. Okay, so now we come to the main problem that we're going to be talking about, the minimum cut problem. So the minimum cut problem is just given a graph, find the minimum weight of a cut in the graph. Okay, so it's just, find this number, the minimum weight of a cut. We're going to denote that number as lambda of G. Okay, so this is really a basic problem in theoretical computer science. Its study goes back at least to the 1960s. First polynomial time algorithm for this problem was given in 1961 by Gomori and Hu, and there's been a lot of work on the minimum cut problem since then. So one breakthrough was in 1998. Karger gave a nearly linear time randomized algorithm for minimum cut. So if there's m edges, his algorithm ran in time m times log cubed of n. And now even in the case of simple graphs, so graphs where all the weights are 1, we even have near linear time deterministic algorithms. So that was first done by Kobayashi and Thorup. It was m times log to the 12th n, I believe. So a large exponent in the log factor, and that was later reduced by Hensinger, Rao, and Wang. Okay, so we're going to be interested in minimum cut in a different model, which is the cut query model. Okay, so what's that? Okay, so we're going to study cut query actually in the deterministic setting. So just a deterministic algorithm that's able to ask cut queries to the graph. So what does that mean? The algorithm can ask any set S, any subset of the vertices S, and it receives the answer, the weight of the cut whose shore is S. Okay, so it receives the answer W of delta of S. Okay, so that's a cut query. You ask a set, you get the weight of the cut whose shores that set. And it's a normal decision tree model, so you can ask these queries in an adaptive way. You can ask a query, you get an answer, then you get to decide what query you want to make next. And you proceed in that way until you've made enough queries to actually output the weight of a minimum cut on the input graph. Okay, and the question is, how many queries do you need in the worst case, over all weighted graphs? And that's yeah, so that's what we're interested in. That's like the deterministic cut query complexity of the minimum cut problem. Okay, so you might think this is kind of a strange query, like why are you interested in these cut queries? And the reason is that studying the minimum cut problem with cut queries is actually a specific case of a more general problem, which itself has been studied a lot in the literature. So let me describe that problem. Okay, so the cut function is actually a submodular function. Okay, so what that means is that, so if we define a function now just on subsets of the vertices V, where let's say C of S is the weight of the cut whose shore is S, then this function has the property that C of S intersect T plus C of S union T is at most C of S plus C of T. Okay, and this property holds for all S and T, and when that happens, your function is called submodular. Okay, so the cut function is also symmetric, because you get the same cut if you take a set or its complement. Those are both shores of the cut. So the minimum cut problem is actually an instance of finding a non-trivial minimum. Non-trivial just means we want to exclude the empty set and the whole universe. So finding a non-trivial minimum of a symmetric submodular function. Okay, so studying minimization of submodular functions, goes back to the 80s. It was first given a polynomial time algorithm there was a polynomial time algorithm given to minimize any submodular function with evaluation queries. That follows from the ellipsoid method, so that was known back in the 80s. And now for this more general problem of finding a non-trivial minimum of a symmetric submodular function, we actually know that that can be done with at most n cubed queries when the size of V is n. So that goes back to Keiran in the 90s, and some very recent results even apply an upper bound of n squared times log cubed n times log of m, where m is an upper bound on the largest value that f takes on, your submodular function f takes on. Okay, so this second one is some very recent results, like a paper of Jiang from Soda of last year, plus some observations that reduce the general submodular minimization finding problem to the non-trivial minimum finding problem. Okay, so minimum cut is the deterministic cut query complexity of minimum cut is a special case of this more general problem of finding a non-trivial minimum of a symmetric submodular function with evaluation queries. And these evaluation queries, that's the usual model in which submodular functions are studied, because the function does have like 2 to the n many possible inputs. So it's usually studied in this oracle model where you have evaluation queries. Okay, so those are the best upper bounds known on this general problem. But the best lower bound is just omega n, and that comes from a very special case. That actually comes from if you want to just tell if a graph is connected or not, a simple graph is connected or not with cut queries, then we know that takes at least omega n many cut queries, and that actually goes back to a result in communication complexity by Heinal, Maas, and Turan. So they show that the deterministic communication complexity of connectivity is at least n log n. Okay, and since you can communicate the answer of a cut query on a simple graph with just log n bits, that implies omega n lower bound on the cut query complexity of connectivity. So it's kind of a very special case. You're only talking about simple graphs. You're only talking about connectivity. So basically, is the minimum cut value 0 or positive? And this very special case is the best lower bound we know on this much more general problem of finding a non-trivial minimum of a symmetric submodular function. Okay, so that's kind of what we're interested in this paper is finding larger lower bounds. So let me just talk about the randomized case for a second. So the randomized case is essentially resolved. Okay, so for simple graphs, Rubinstein, Schramm, and Weinberg gave a randomized cut query algorithm that computes minimum cut after n times polylog many queries. And a few years later, Mukhopadhyay and Nanonkai gave an algorithm for weighted graphs with the same complexity n times polylog. Actually, it's interesting, these two papers use very different techniques. Like the Mukhopadhyay and Nanonkai paper follows Kargar's algorithm that I mentioned from 1998, the first linear time randomized algorithm for minimum cut. And we also know nearly omega n lower bound, so omega of n log n over log n. And that result again follows from communication complexity. Okay, so up to a polylog factor, we understand the randomized cut query complexity of min cut. Okay, whereas the deterministic case is still wide open. So the best lower bound, as I mentioned, comes from this communication result on connectivity. So that's like C times N for some C. Oh, I'm sorry, that's it's a typo here. This is not C less than N. This is C less than 1. Okay, so that's the best lower bound. And there's a recently an interesting paper by Grauer et al. And they introduced this notion of cut dimension that we're going to be talking about today. And they used that to show a lower bound, strictly larger than n. So they showed a lower bound of 3n over 2 minus 2 on the deterministic cut query complexity of minimum cut. So that's, up until our work, that was the best lower bound that was known. As far as upper bounds, I don't know anything besides just the trivial algorithm of querying all the edge slots, which has complexity n squared, order of n squared. Okay, so that's basically the state of affairs. We have this huge gap between the lower and upper bounds. And so, that was where we started, hoping to close this gap. You'll see how far we got. Okay, so we're going to talk about this notion of cut dimension that was introduced by Grauer et al. So what is the cut dimension? Okay, so independently of showing lower bounds on cut query complexity, I have to say this cut dimension, it's really a beautiful linear algebraic quantity. And I'm kind of surprised that cuts have been studied for so long. I'm kind of surprised that it wasn't introduced earlier. But anyway, here it is. So let's say that our graph has m edges. Okay, so for a cut delta of s, I'm going to let chi of s be its characteristic vector amongst the m edges of G. Okay, so just order these m edges of G arbitrarily, and for every cut delta s, we can make a Boolean vector of dimension m, and basically just for every edge of G, this vector just indicates if that edge participates in the cut delta s or not. Okay. All right. So for every cut, we have this Boolean vector. So now just take all the minimum cuts of G, look at their, I'll call these vectors cut vectors. Okay, so take all the minimum cuts of G, look at their look at their cut vectors, and look at the dimension of the span of those vectors. Okay, that is the cut dimension of G. Okay, and we're going to call it CDIM of G. So let's look at an example again. So here's the same graph that we had before. So I'm just going to, let's say this graph has 8 edges. I'm just going to take them in lexicographical order. Okay, so here's the ordering. So if we look at the star cut, defined by 1, so again, the edges in that cut are 1, 2, 1, 3, and 1, 5. So those are just the first 3 edges in my lex order. So the cut vector is 1, 1, 1, and then the rest are all zeros. If I take the cut with shore 3, 4, then the edges participating in that cut are 1, 3, 3, 5. So those are the second edge in my order, and the second to last edge in my order, and also 2, 4, and 4, 5. So 2, 4, that's 1, 2, 3, fourth edge, and 4, 5, the last one. Okay, so we basically put ones in those positions, the second, fourth, second to last, and last, and that's our cut vector corresponding to the shore 3, 3, 4. Okay, so I do that for all the min cuts. So again, in this graph, the min cuts are given by all the star cuts, and the cut with shore 1, 2, and the cut with shore 3, 4. So so there's 7 such min cuts. I put them as rows of a matrix here. And it turns out that these rows are all linearly independent. Okay, so I mean, you can just do Gaussian elimination on this and see that. So that means that the cut dimension of this graph is 7, right? So again, what did I do? I just I look at all the min cuts of the graph. I look at their corresponding cut vectors. I put those as rows of a matrix, and then I look at the rank of this matrix. That's the cut dimension. Okay, good. Okay, so besides just being kind of a neat measure of complexity of the cuts of a graph, Grauer et al. Show that this cut dimension is a lower bound on the deterministic cut query complexity of minimum cut. So the cut dimension of a graph G is a lower bound for any G. Okay, so you can basically maximize over all G to get your lower bound. Okay, so we actually observed that it's a lower bound in an even stronger model, what we call the linear query model. So here, instead of just asking the value of a cut, you can actually query any real vector in choose 2 dimensions, and you receive the answer, the dot product of your query and the weight vector of the graph. Okay, so so this can be a much stronger model than cut queries. Like you can see, if you, for example, if you have just a simple graph, then you can actually recover all the edges with just a single linear query, right? Just by querying the vector 1, 2, 4, 8, 16, etc. Okay, so this can be quite a powerful query, but as far as the cut dimension, it's still a lower bound on this more powerful kind of query. Okay, so in fact, the cut dimension is a lower bound not just on the deterministic cut query complexity, but also on the certificate complexity. Okay, so this actually is not a point that we make in our paper. So I only realized this later. So actually, thanks goes to Simon, Sagnick, and Downupon, because I was talking with them, and we were talking about showing larger lower bounds for deterministic cut query complexity. And we were just like, okay, how could you do that? Well, you take out the query complexity survey by Berman and DeWolf, and you say, okay, what methods do we have for showing lower bounds on deterministic query complexity? And the first one there was certificate complexity. So we started talking about, okay, how would you show lower bounds on certificate complexity? And then I kind of realized, oh, well, this is exactly what we're doing with the cut dimension. Okay, um, so let me explain what do I mean by certificate complexity in this context. So let's say that you have a graph G. So the linear query certificate complexity of G is the minimum K such that there are queries x1 through xk. Again, each of these is just a real vector and then choose 2 dimensions. So the minimum K such that there exists some K queries that have the property that for any weighted graph G prime, if G prime agrees on all the answers to the queries with the answers given by W, in other words, the dot product of xi with W is the same as the dot product of xi with W prime for all I, then they must have the same minimum cut. Okay, so these queries kind of witness the value of the minimum cut of G, right? Because any other graph that has the same answers on those queries must have the same minimum cut. Okay, so that's the certificate complexity. Okay, so let me go ahead and sketch to you why cut dimension is a lower bound on certificate complexity. Okay, so we just need a little bit of linear algebra to see this, but let's go through it. So again, G is our graph with weight vector W, and let's say we have queries x1 through xk. So I like to think about this in the following picture. So I package these queries as the rows of a matrix. So let me call that matrix A. And now what are the answers to the queries? When my input is G, with weight vector W, well, it's just the result of this matrix vector multiplication. Right? Those are the answers to my K queries. Okay. Okay, so what's nice about this picture? Well, you can see that what graphs are going to have the same answers to the queries as G has. Well, you see that if I take any vector in the kernel of A, so say I have some vector Z in the kernel of A, right, in the kernel. Okay, then if I modify my weight vector to a weight vector W prime, which is W plus Z, then that graph with weight vector W prime is going to have the same answers to the queries as G does. Okay, so the question is, just can we find something in the kernel such that W plus Z, well, it has to be non-negative, so that's our first restriction, because we want this to define a valid graph. So can we find some Z in the kernel such that W plus Z is non-negative and also has a smaller minimum cut than G does? Okay, so the claim is that if K is less than the cut dimension, then yes, we can always find such a Z. So let's see why that's the case. So the rank of A is of course at most K. So if K is less than the cut dimension, then there must be a cut vector. So some minimum cut, its cut vector must not be in the row space of A, right? Because the cut vectors of the minimum cuts, they span a space of cut dimension of G. Okay, so let C be a cut vector of a minimum cut that's not in the row space of A. Okay, so just a general linear algebraic fact is that actually every vector in dimension n choose 2 can be written as the sum of something from the row space of A plus something from the kernel of A. And moreover, this is an orthogonal decomposition. So Y and Z here will be orthogonal. Okay, so write C as Y plus Z, where Y is in the row space, Z is in the kernel, and these vectors are orthogonal. Now, since C is not in the row space, that means that Z has to be not the all zero vector here. okay? Okay. Okay, so that means that, again, we have C is equal to Y plus Z. Z is not the all zero vector, and Z is in the kernel, so A times Z is the all zero vector. And the dot product of C with Z, since Z is orthogonal to Y, that's just the norm of Z squared, and that's going to be positive. Okay, so what that means is that we can take some epsilon, some small epsilon, and just perturb W to W minus epsilon times Z. And we can take epsilon small enough so that this is going to be a non-negative vector. And at the same time, in the graph whose weight vector is this, the cut corresponding to C is going to have a slightly smaller value. Okay, and since C was a min cut, this is going to mean that this graph G prime has a smaller min cut than G does. Okay, so that means that if you make less than K queries, then you don't have a certificate, right? Because I can find this other graph G prime that has the same answers to all the queries, but a different min cut value. Okay, and if you're not familiar with certificate complexity, you can also see that that's a lower bound on the query complexity, because basically, as your algorithm makes queries, I always answer the query according to G. And if you stop making queries, if the number of queries you've made is less than the cut dimension, then I can come up with this other graph G prime, which has the same answers to all the queries, but a different minimum cut value. Therefore, your algorithm, can't output the right answer, because the input, according to your view, could be G or G prime. Okay, so that's why cut dimension is a lower bound on certificate complexity or deterministic query complexity. So that's kind of again, just motivating the usefulness of this cut dimension. Okay, so again, just recapping, I just showed that the cut dimension is a lower bound. The cut dimension of a graph G is a lower bound on the linear query certificate complexity of G. And in particular, if you if you can actually maximize overall graphs G, the cut dimension of G will be a lower bound on the deterministic linear query complexity of minimum cut. Okay, good. All right, so now let's actually get to our results. So our first result exactly characterizes the cut dimension. So we showed that the cut dimension of any in-vertex weighted graph is at most 2n minus 3. And for every n greater than or equal to 2, we construct graphs that realize this bound, that have cut dimension 2n minus 3. Okay. So our second result is that we can actually show a bound larger than the cut dimension. So if we, the cut dimension is a lower bound on the certificate complexity, but by just looking at certificate complexity itself, we can actually show a slightly larger lower bound. So we're able to show a lower bound of 2n minus 2. Okay, so this is just kind of a proof of concept at the moment. It just shows that certificate complexity itself is not limited by the same upper bound of 2n minus 3. Okay, and this bound of 2n minus 2 is currently the best known lower bound for this more general problem of non-trivial minimization of a symmetric submodular function with evaluation queries. Okay, so let's talk about this theorem 1. So the key concept to both the upper and the lower bounds is an idea of what's called a cross-free family of cuts, of minimum cuts. Okay. Okay, so of course, every cut, it has two shores. So to to make the shore corresponding to a cut unique, from now on, I'm just going to pick some distinguished vertex V naught and V, and I'm always going to take the shore that not containing V naught, okay? All right, so what is a cross-free family of cuts? Okay, so take a set of cuts, let's say delta of S1 through delta of SK. So this is cross-free if and only if for every two shores, SI and SJ, either they're disjoint, so SI intersect SJ is the empty set, or one is a subset of the other. So SI is contained in SJ, or SJ is contained in SI. Okay, so such a family of sets, if I just look at these shores, that's known as a laminar family. So again, every two sets in this family, they're either disjoint or one is contained in the other. Or one is contained in the other. Okay, so just to reinforce this idea, we can look at a picture. So a laminar family, it can always be represented by this tree-like structure. So here an arrow indicates inclusion. So here I have the universe V. So S1, S2, S3, they're disjoint. Okay, and then I have some sets that are subsets of S1. A set here, there's a subset of S6. Okay, so this property of being a laminar family, it always allows this tree-like decomposition. Okay, and you can actually use this property, this tree representing the structure of the family, to show that the cardinality of a laminar family, when the universe is of size n, is always at most 2n minus 1. Okay, so this is this is a known result. You can find this in textbooks. Okay, so but our sets, since they are shores, they're not just an arbitrary laminar family. They basically have two additional properties. The first property is that it's complement free. That's again because for every cut we just take the shore not containing V naught. Okay, so we're not going to have the complement of that set. And also, we don't have the whole universe, right? Because the whole universe doesn't define a cut for us. So once you have these two additional properties, you can basically knock the upper bound down by 2. So you can show that a laminar family that's complement free and doesn't contain the whole universe is always of size at most 2n minus 3. Okay, and you can actually achieve that bound. So again, if we go back to our running example here, the minimum cuts are all the star cuts, and 1, 2, and 3, 4. So if I write all the shores as sets not containing 1, so basically the star cut corresponding to 1, it becomes the set 2, 3, 4, 5. Then we have the star cut corresponding to 2, 3, 4, 5. So this, is a shore for my cut 1, 2 here, etc. So you see here the tree-like decomposition, and let's see, we have a graph on 5 vertices. So 2n minus 3 is 7, and indeed we have 7 sets here. So we actually achieve this upper bound. Okay, good. All right, so now we've shown that the size of any cross-free family of cuts is at most 2n minus 3. And now we can use this very nice lemma of Jane, going back to 2001. So he says the following. So if you have a graph G and a subset, which is a maximal family of cross-free minimum cuts, so any other minimum cut crosses some cut in your family. That's what we mean by maximal. Then actually every minimum cut is a linear combination of cuts from this set L. Okay. So this is a very nice lemma, and basically uses a combinatorial uncrossing argument. And the fact that min cuts have this special structure, which is that if delta S and delta T are min cuts, then because of submodularity, delta of S, and they cross, then because of submodularity, delta of S intersect T and delta of S union T have to be min cuts as well. Okay, so you kind of use this property in this combinatorial uncrossing type of argument to show this lemma. Okay, so that's basically it. So now we're done, right? Because we just take this maximal cross-free family of minimum cuts. It has size at most 2n minus 3, and the lemma of Jane says that every minimum cut can be written as a linear combination of the cut vectors from this set. So that gives an upper bound of 2n minus 3 on the cut dimension of any graph. Okay. Okay, so now let's go to the lower bound. So now we want to construct graphs with cut dimension 2n minus 3. So for this construction, we're going to consider complete weighted graphs. Okay, so we're going to have an edge between every two vertices, and that edge can have a weight. Okay, but it's going to have a positive weight. It's not going to be 0. Okay, so the main lemma that we show for the construction is that if we have a complete weighted graph and L is a maximal family of cross-free minimum cuts, then actually the cut vectors in L are linearly independent. Okay. So we basically know that the vectors from a cross-free family, they're going to be linearly independent. Okay, so this basically reduces the problem to finding a complete weighted graph that has a cross-free family of minimum cuts of size 2n minus 3. Okay, so we basically want to come up with weights on this graph so that if we look at all the set of minimum cuts, there's actually a cross-free subset of size 2n minus 3. Okay. So that's still not really trivial to do that. So we have another lemma, which is very helpful for that task. And that's that, so if we start out with a cross-free family of cuts in the complete graph, and if all those cuts have the same value, C, in some weighting of the complete graph, then C must be the minimum cut value in that graph. Okay? So there can't be any cut with smaller value. Okay, so that kind of makes our problem simpler because now all we have to do is solve a linear program, right? Basically what we want to do is we want to come up with a weighting of the complete graph. Okay, so let's look at it this way. So we're actually going to start out with, a family of cross-free cuts in the complete graph of size 2n minus 3. Okay, so those are the cuts that we want to be minimum cuts in our weighted graph, and the weights we still need to cook up. Okay, so we have the cuts that we want to be minimum cuts. So now we just need to find a weighting so that all those cuts have the same value, right? Then this lemma tells us that will be the minimum cut. And the other thing is we need to ensure that it's a valid graph. So we need to ensure that the weights are all, well, let's say we want them to be positive. So without loss of generality, we can just assume that they're all at least 1. Okay. So this basically kind of turns the problem into a linear program. So you want to find a weighting which is at least 1, and this weighting satisfies a linear system of equations, which is basically that the weight of all the cuts in your cross-free family have the same value. Okay. So this is a linear program, and we actually are able to explicitly solve this linear program. Okay, and we basically do that by, again, we start out, with this Crossfree family of cuts of size 2n minus 3. And we basically look at the tree decomposition of the shores, and we kind of view this linear program as like a flow problem on this tree, and we're able to solve that flow problem explicitly. Okay, so yeah, so just to give you an example of, that we can solve this problem. So here's a bigger example. So a graph on 8 vertices. And, again, we start out with, this laminar family of shores that we want to be the minimum cuts, and then we cook up the weights to make that happen. Okay, so here the red edges have weight 8, and you see that there's kind of a perfect matching of the red edges. And that's because we said, okay, I want 1, 2 to be a minimum cut, 3, 4 to be a minimum cut, 5, 6, 7, 8 to be a minimum cut. And then these green edges have weight 3. Yeah, so so this is a graph that has cut dimension 13, which again is 2 times 8 minus 3. Okay, so for the theorem 2, so I'm not going to talk too much about it. It's a little bit involved, but just to show how we can go beyond the cut dimension. So we actually give a linear algebraic characterization of the certificate complexity, of this linear query certificate complexity of minimum cut. So let me just at a very high level describe what this characterization is. So now basically, instead of just considering cut vectors corresponding to minimum cut, we consider all cut vectors. Okay, so we basically think about this matrix that has a row for every cut vector. Okay, so now this matrix has 2 to the n minus 1 many rows. Okay, and now you're actually going to be allowed to perturb each row, and by how much you perturb the row is determined by the weight of that cut minus the minimum cut value. Okay, so cuts that are actually minimum cuts, you can't perturb at all, right? Because that difference is 0. Cuts that are close to minimum cuts, you can perturb a little bit. Cuts that are very far away, you can perturb a lot. Okay, but already, right. And then the question is just, what is the minimum rank of this matrix under these perturbations? Okay, so again, you can see this is at least the cut dimension, because the minimum cuts you're not allowed to perturb at all, right? So those vectors, have to be in the row space of this matrix. So the rank is going to be at least the cut dimension. But it turns out you can actually show larger lower bounds by considering cuts that aren't minimum cuts, at least by +1. Okay, so that's what we do. And as you might imagine, there's a huge matrix, and bounding the rank under these perturbations, it's not a very easy task. So basically how we do it in this case is we just look at the complete graph on 4 vertices. In that case, it's not too hard to show that the minimum rank of this matrix is 6. That's actually optimal, right? Because the complete graph on 4 vertices, it just has 6 vertices, 6 edges. So the query complexity is obviously at most 6. So we show a lower bound of 6 for this complete graph of 4 vertices, and then we basically kind of do a direct sum type construction. Okay, so we just glue many copies of K4 together at a single vertex. Okay, and the the matrix of cut vectors for this direct sum, it kind of has a lot of copies of the matrix for just one case, and yeah, we're kind of able to show this direct sum type bound. I mean, I should highlight that it's not a general direct sum. It is tailored to this particular case, but in this particular case, we are able to show this direct sum type lower bound. Okay, so open problems. What is the deterministic cut query complexity of minimum cut? So again, asymptotically, the situation is still the same. You know, we have this omega n lower bound, order n squared upper bound, still wide open. What what the true value is. And you know, something I'm very curious about. You know, how good a lower bound can this certificate complexity bound be, right? So we showed that the cut dimension is at most 2n minus 3, but how about certificate complexity more generally? You know, can you use that to show a super linear lower bound? So that would be very interesting. Okay, so that's all I have. Thanks for your attention. Bye bye.